Let's talk acids and bases now. These are some of the most important compounds in chemistry, in general chemistry, and also definitely in organic chemistry. So let's go first through all the definitions that we know for acids, bases. They don't change from general chemistry. They are still the same. So there are three definitions that we talk about: Arrhenius, Bronsted-Lowry, and Lewis, right? So Arrhenius theory is when the acid is the proton donor and the base is the hydroxide donor. Okay, and so that would be the first definition, Arrhenius definition. Most times this will work for us, okay, but sometimes when it doesn't work, then we use the Bronsted-Lowry theory, which is the acid is still the proton donor. Okay, so that hasn't changed from Arrhenius, but what has changed is the base is now the proton acceptor. Okay, so Arrhenius theory with the base as the hydroxide donor works really well because a lot of the bases are actually hydroxides. Okay, so it works quite fine. But in some cases, like ammonia, where it doesn't have a hydroxide, yet it is still a base. So now we have to change the classification a little bit, not to suit us, but to help us with the properties, okay, of substances. And so the base now is the proton acceptor because that's what it does when you react it with an acid. And then finally, the third theory is the Lewis theory. And the Lewis theory, as usual, of course, has to do with electrons. Acids are electron pair acceptors and bases are electron pair donors. And you will see that the example I've given here is that of ammonia again. So ammonia here in the Bronsted-Lowry theory is proton acceptor, but here it is an electron pair donor. So in case you're wondering like how it is in both, well, it depends what it is reacting with. Okay, and so you classify the base as a proton acceptor, as a Bronsted-Lowry base, depending on what the acid is. Okay, and the same thing happens for ammonia. Depending on what the acid is, that's how you will classify the base ammonia as Bronsted-Lowry or Lewis. Okay, and in the beginning, I am going to ask you to classify the acids and bases as Bronsted-Lowry or Lewis, so that way you kind of know what you're looking for. Okay, and what does that mean, what you're looking for? It means, are you looking for a hydroxide? Are you looking for electron pairs? What are you looking for? Because when we start doing reactions of acids and bases, those are the things you have to look for. Okay, is am I looking for a proton? Am I looking for an electron? Okay, so these are the things you have to pay attention to. So depending on what kind of an organic substance there is, that is how you classify them. Okay, because when we do reactions, and you know, we've done some reactions before in general chemistry. I mean, you've done plenty, acid bases, redox reactions, precipitation, all those kind of reactions that we did. All of those reactions, you know, they are classified to help us so that, you know, we don't get all jumbled up in our mind, and we know when we look at a reaction, this, okay, so now we can focus on the fact that this is an acid-based reaction or this is a redox because electrons are being exchanged. But here now you can see that a Lewis acid base can also exchange electrons, but this is not an exchanging, this is actually forming a bond. Okay, so I mean, there's slight differences, which is, you know, why we're learning about all these things. Okay, so these are the definition. One thing I want to remind you of is something you should keep in mind always, is that when we are talking about Arrhenius and Bronsted-Lowry acids, we say it's a proton donor, okay? And we all understand what a proton is. It's H+. And why it is H+ is because proton has only two particles, right? An electron and a proton. So if the electron is gone, the only particle remaining is a proton. So sometimes H+ is also called a proton. I will not say sometimes, I think almost always it's called a proton. So that's what we call acids. But what happens is that most of the times Arrhenius and Bronsted-Lowry acids are actually made in water. If they are made in water, this H+ will combine with water and give H3O+. Okay, so which means that you never find H+ anywhere. So we know it's a proton donor because it's going to give a proton, but that proton donation happens right away to water giving us the hydronium ion, which is H3O plus. So in an acidic solution, you will always have H3O plus and not H plus. H3O plus is also water. If you remember, when you calculate the pH, pH is minus log of H3O plus. So you can write H plus also, but we tend to write more H3O plus in there. So where is that coming from? Now you know. Okay, it's coming from the water. And one other thing I want to clarify here for you for Arrhenius and Bronsted-Lowry is that these acids are always made in water. Okay, so for example, if you have HCl, HCl by itself, if I weren't to write anything in front of it, you would call it hydrogen chloride, because HCl is a gas and you call it hydrogen chloride. As soon as I write AQ in front of it, okay, which I have not over here, but if I were to write AQ in front of it, suddenly this now changes everything, because now HCl is dissolved in water and it becomes an acid. Okay, so the pH of hydrogen chloride is nothing, whereas the pH of HCl is going to be lower than 7. Okay, depending on how much HCl I have in there. So I just want to clarify that for you. I didn't write the AQ over here because generally we tend not to write. We kind of skip those kind of things. It happens, you know, but please know, okay, that all these acids are made in water. And one other term I want to remind you of is amphoteric substance. Okay, an amphoteric substance is something that behaves like an acid and a base, both. So depending on what you're reacting it, what you're treating it with, it can behave like an acid or a base. Okay, so be aware of this term because we will use it, and you know, organic compounds also sometimes tend to be amphoteric. The classic example of an amphoteric substance that you know so far is water. All right, so here are some examples of the acids and bases, the Bronsted-Lowry acids, the Bronsted-Lowry base. Lewis acids are covered in another presentation because they're a little bit different. These two you have encountered before and dealt with, so they're more familiar to you. So inorganic acids will be anything that gives a proton, right? So hydrogen is shown right here for us, which is HCl, hydrochloric acid, sulfuric acid, nitric acid, and so on and so forth, okay? Organic acids are shown over here. The one you're most familiar with is the first one, which is also called acetic acid. And let me write the name for it, although I think you already know it because you have dealt with it before. So acetic acid is something that we deal in Gen Chem 2 a lot when we study equilibrium. So that's that, and then you will see all the other acids. So you're already familiar a little bit with organic functional groups, so you will see that almost all of them have carboxylic acid group in them. See, the name itself says acid, right? Carboxylic acid. So they're all acids, okay, pretty much. So a few things over here, okay, to note is that the Bronsted-Lowry acids will have a proton to donate. Now you will not see that proton, you have to look for it, okay. It will, sometimes the H plus is just like H plus in a reaction, but in something like this, in a molecule, you have to find that H, and usually for inorganic acids it's pretty easy because that H is written right in the front. So HCl, H2SO4, HNO3, all the hydrogens that are written in the front, these are all the H pluses that are going to go away. Okay, that's the proton donor. In the case of organic acids, things are going to be a little bit different for us, okay? And that's why we have this whole chapter, because organic acids are a little bit different. And so you will see there is no H in the front here, CH3COOH. The acidic proton is actually this one. Okay, the last one. It's not in the beginning. In Gen Chem, you know how we write things. It's a little bit different. Acetic acid is written like this: HCC2O2. Let's see, what is it? 3 H3O2. Okay, something like this. You see, I can't even write it because I'm an organic chemist and I have a really hard time with that. Okay, so HTC2. H3O2. Okay, so that's how it's written, so that in Gen Chem you're aware that this is the acidic proton, because right now this is the acidic proton, which is at the end, and this is actually the correct way of writing it because it's an organic acid. But anyhow, so now we are getting familiar with organic acids and everything else, so you know, we'll be fine. You'll recognize a lot more. All right, so acids generally are going to be neutral or they will be positively charged. So in case you have a hard time recognizing acids, hopefully by the end of the chapter, not so much, okay? But, look for protons and you look for positively charged substances. That will help you. Bronsted-Lowry bases, now the one on the left you're quite familiar with. So we have water, we have ammonia, and all the hydroxides. I haven't written all of them, but there are plenty of hydroxides. Almost all hydroxides are going to be bases, okay? So the hydroxide is the Arrhenius theory, right? OH donors, those are the bases. As far as the organic bases are concerned, you can see that they all have nitrogen in them, and the nitrogen is coming from the ammonia here, okay? So you take away one hydrogen, put a carbon group in there, and it becomes an organic base. So generally we say organic bases, these are all the amine functional group, okay? So carboxylic acids were the acids, the amines are going to be the organic bases, okay? And then I gave you here some more examples for the Bronsted-Lowry bases, and if you don't remember them, it's okay for now, because as we go on you will learn about why they're considered to be bases. Right now they're just examples and they're there for you because negatively charged acetone, like this molecule, I mean, like where is the base? But remember, bases are also proton acceptors. Okay, so the proton acceptor is right here, the oxygen. Okay, that's the proton acceptor. Anyhow, so a little bit different here. So I've written it here for you that Bronsted-Lowry bases will have a lone pair of electron or a pi bond. So here is the lone pair of electron, here is the lone pair of electron on nitrogen, and then the pi bond is right here. Bases will be generally neutral, or they will be negatively charged. So right here is the negatively charged. Acids are positive, bases are negative because they need electrons, right? So that's how it works. So these are some of the examples, and we will learn more as we go on. Okay, so let's go a little bit deeper into Bronsted-Lowry and even Lewis, acid base. So generally what we do in organic chemistry, okay, now we're getting a little bit more into organic, is that we tend to write our reactions like this. Okay, so you have seen reactions like this, of course, before, but not with the arrows. Okay, but what we tend to do a lot of times is that we write our reactions in arrows. Again, not all the time, okay, but when we are trying to show what is moving where, okay, especially in electronic terms, okay, or in proton terms, because in acid-base reaction, the proton is moving, right, from the acid to the base. So we have to show all of these things. To show all these things, we have to show arrows. And so what I've shown you here is an acid-base reaction where HA is the acid, B is the base, and then these are the products on the right hand side, which the acid gives you the conjugate base and the base gives you conjugate acid. So the most important thing here that I want to show you is the arrows. Okay, so the pink arrow that we have is going from the base, which is electron rich. You can see the lone pair of electron, and it is picking up a proton. Okay, so this is a proton acceptor, and the acid here is HA, which tells you that this is a normal Bronsted-Lowry kind of an acid because that's a proton donor. So which means it is giving the proton. When we say it is giving a proton, what does that mean for us? Again, the proton was H+. H+ means that a hydrogen is leaving without its electrons. So remember, we have this bond right here. This bond has two electrons. Okay, one belongs to the hydrogen, one belongs to A, whatever it is, X, or sorry, not X, like chlorine or fluorine, whatever it is. So one belongs to hydrogen. It means what? H+ means that it is leaving even that hydrogen, that electron with A. So here you can see A has two electrons, okay, because it got the one for hydrogen as well, and it had the one from A already. So this line, which was an electron pair, now we just show that as a lone pair of electrons. Okay, so the base is picking up a proton. The proton is leaving without its electrons. Okay, so how do we show that? Is the second arrow that I have shown you here in blue, and that arrow tells you that these two electrons are moving to A. Okay, so that's what we show over here then, okay, that A has the 2 electrons. So now what do we have? In the product side, we have A with the 2 electrons, okay, that are left from the bond that broke. And then we also have B, which has picked up a proton. Okay, so now B is going to be positive because now it's become acidic. Okay, remember, B here is just a lone pair of electron. When it picks up H plus, you just add them up together and you still get the plus also, okay, in there. So it's a mechanism of a reaction where you show how the bond is forming and how the bond is breaking. Which is the bond that formed here? The bond that formed here is this one, right, between B and H, because the boron picked up the proton, not the boron, gosh, the base. Okay, B for boron, right? Okay, so the base picked up the proton, so it became the conjugate acid. So this arrow shows you how the bond is forming. This arrow shows you how the bond is breaking. I'm not saying you have to get color coded. I have tried to be consistent, but again, it doesn't work all the way. Usually every book will just have black arrows. One of the most important things we have to do in organic chemistry is identify the acidic proton, okay? Because as I said when I showed you the examples, is that things are not clear all the time, okay? So things may not look like an acid at all, but they are acids. Inorganic acids are really easy, right? You know exactly what you're looking for, HCl, H2SO4. You know where the hydrogen is. But for organic compounds, you have to pay a little bit attention. Okay, so the best way to look for in an organic compound is actually to look for polar bonds. Okay, wherever you have a polar bond, that hydrogen is going to be the acidic hydrogen. Okay, so let's look at carboxylic acid, okay, to begin with. So you have a CH3 and you have a COOH, which means you can have two kinds of protons. You have a proton here, which is the red one, and then you have protons here, 3 protons. But the bond between carbon and hydrogen is not as polar as it would be between oxygen and hydrogen. So the bond between oxygen and hydrogen is more polar, and therefore this hydrogen is going to be the acidic hydrogen. Now, how strong is that acid? That's a whole different thing, right? That's the calculation of pHs, which we have done in Gen Chem. That's a different thing. But at least it's more acidic than this one because the CH bond is not as polar. The same thing happens for an alcohol group. In an alcohol group, they have an OH bond, you have a CH bond. So again, the OH bond is a lot more polar than the CH. So this is the acidic proton. So when we're looking at an alkane, alkane is no polar bonds, right? CH, and they're also both the same, CH and a CH. So I've highlighted both the hydrogens here because both of these hydrogens are equally acidic. Now, how acidic? Again, that's a different thing. That's the next presentation, okay? So that's the next lecture. We're not doing that right now. We're just identifying the acidic proton. Obviously, this proton is not going to be as acidic as this one, right? So we have to talk about that eventually. But right now, we're just focused on what kind of proton is an acidic proton. Then here is an aldehyde. Now, why did I write an aldehyde? Because aldehydes are a functional group, right? So here is an aldehyde. Oh, I have it drawn here. So look at the bottom, and here then at the bottom, where you can see that I have written out the 3 hydrogens for you. Now, this hydrogen is part of a functional group. So that hydrogen is not going to be available, all right, for reaction. The aldehyde proton belongs to the aldehyde functional group. Now you say that hydrogen here belongs to the alcohol functional group, but here the hydrogen is attached directly to the oxygen. So that's a little bit different. Here you see this hydrogen is attached to the carbon, all right, not to the oxygen. So it's a little bit different. So it's a functional group. And so that connectivity makes aldehyde a functional group, which means that this proton is not available for reaction, which means you only have these 3 protons as acidic proton if you were considering that to be. So if I ask you where is the acidic proton, you just label the one that is the most probable acidic proton. You will not label this one as an acidic proton in case of an aldehyde. Now if it was a ketone, So ketones don't have that issue where that carbon has a hydrogen. So any of these protons can be the acidic proton then, okay? Again, we're not talking about whether it's strong or not. We're just talking about whether it is an acid or not. That's what we're talking about. So look for polar bonds, okay? That will help you identify if your proton is available as an acid or not. Okay, conjugate acid-base pairs. This is a review for us from back in Gen Chem because we know that conjugate bases are from acids. So you can write it the other way if that helps you. Acid gives you a conjugate base. Base gives you a conjugate acid. Okay, you should always write things in your own words, whatever helps you understand it better. I was focusing on conjugate base, so I wrote that first. But otherwise, if you want to focus on what an acid gives you can write it that way also, okay? Because it's the same thing. Acid will give you conjugate base, base will give you conjugate acid. The other key thing here is a really important one, which I've written over here, and that is that if you have a strong acid, it's going to give you a weak conjugate base. If you have a weak acid, you'll get a strong conjugate base. Now, why is this important for us? Okay, this is important for reactivity. We need to know if reactions will occur or not. So when you look at an acid base, okay, acid base reaction, my question will be to you at some point, will this reaction occur or not? Because even you should know that if you have two chemicals, are they going to react or not? Okay, you should be able to predict that. That's the whole point of chemistry, right? We're learning about reactions. So if you are given an acid and a base, you should be able to predict that. So these kind of things will help you to understand whether a reaction will take place or not and to predict it. Okay, so a strong acid gives you a weak conjugate base. A weak acid will give you a strong conjugate base. Conjugate bases are the other way also, okay, which means they, a strong base will give you a weak conjugate acid and a weak base will give you a strong conjugate acid. So these are very important pairings that we need to understand. And it's a good thing that there is a little bit of a trendy thing here, right? Strong gives you weak and weak gives you strong kind of a thing. Write it in your own words, okay? So you have this with you so you don't confuse this. Okay, so since you've done this before, here's a reaction just to kind of help you again how to write conjugate acid-base pairs. So here is an acid, here is a base. Now this is just a simple reaction between an HCl and water. Okay, so I said to you hydrogen chloride, when dissolved in water will give you acidic water, sort of acid. And HCl in solution. So what do you really have in solution at that time? So this is what we have. HCl dissolving in water will give you H3O plus and Cl minus. Okay, so how does this work? H2O is going to be the base. It's going to pick up a proton. So I wrote this reaction earlier on. Okay, so I explained it to you how it works. So oxygen is picking up, not the H. So water also is an acid, don't forget that, okay? Because it's an amphoteric substance. So be aware of that. So here are the electrons that are picking up this proton. That's how you're getting the H3O plus, okay? Now, if the acid is here, the acid is going to give you a conjugate base. So I have labeled all of these things for you, showing you either with the arrow what's going on. It's also losing a proton. So I've tried to be as descriptive as possible in this reaction so you understand what's going on. The H2O, since it's picking up a proton, it becomes H3O plus. Now this base becomes a conjugate acid. Okay, let me give you a very simple thing over here. Okay, let's remove all of this writing that I have done so I can focus you on something here that's very interesting. So acid is becoming the conjugate base, base is becoming the conjugate acid, right? That's what we just said. Now I want you to focus on the conjugate acid for a second. Okay, look at the conjugate acid. It's H3O plus. H3O plus, for all practical purposes, is an acid. Okay, so for you to even think about that as a base would be, okay, not good. I'm going to be polite. Okay, it's not going to be good. So H3O plus is going to be the acid. Okay, now once you have identified that this is the acid, automatically this is the base. Okay, All right. Now I need you to think back into what I was talking about a couple slides ago when I was explaining the acids and bases to you, right? In the acids, I said to you acids will be positive or neutral and bases will be negative or neutral. So here is your base that is neutral. Here is your base that is negative. Okay, do you see that now? So that is how these reactions work. Okay, the more you understand these reactions, the easier it will be for you to write these reactions. Okay, when I explain all of these things, and I'm taking my time to explain this, that's the fun thing about making a video, is I can explain in a longer time rather than in a class where I'm limited. Okay, so try to understand, okay, all of these reactions as much as possible. So classify everything. The first thing you do for any reaction is classify something into an acid and a base. Once you know what the acid is and what the base is, then you will see it's a lot easier for you to write the products then. Okay, so let's look at the bottom one here. Here's ammonia and I'm reacting this with water. I deliberately took these two reactions because they're both with water, and water is an amphoteric substance, so I kind of wanted to show you, okay, that here water is a base in the top reaction, but it's an acid in the bottom reaction. And so if water is the acid, okay, in the bottom reaction, then the water is going to be then giving the proton, right? So this is the proton donor. Let me just write H plus, okay, donor. So if it's giving the proton, NH3 is picking up the proton, okay. So if it's picking up a proton, this is the arrow that's going to happen. So see, now you have NH4 plus, okay, because now it picked up a proton, so which means it's just added on an H plus. So NH3 plus H plus gives you NH4 plus. Just simple math, right? Okay. And then since H2O has lost a hydrogen, it's got extra electrons now, so now you have OH minus. So again, the conjugate base pairs over here, let me erase all of this so we can see clearly. And so the conjugate acid base pairs are pretty clear because base will give you conjugate acid and acid will give you conjugate base. Base is the negative, acid is the positive. Once you start seeing these kind of reactions over and over again, you will see that things will become a lot easier. Okay, so, and I never say that I am the only one you should be listening to. You should be listening to other lectures. You should be reading books also about these. So you can see a variety of reactions. There's only so much I can do. Okay, so the rest really you have to kind of pick up on that. So here are some examples of acid base pairs. So this is how it works. Here is the acid, okay, and that's why you need to recognize where's the acidic proton, so that when you lose the proton for the acid to write the conjugate base, you lose the correct proton. You don't lose from the H3, CH3, you lose it from the OH, okay, over here. So then O minus is going to be the conjugate base. For H2O, we did that over here. That's the conjugate base. For NH3, you're losing a proton. When you lose a proton, you're going to get NH2, okay? So conjugate base always going from here to here is minus H plus. So minus H plus meaning almost everything is going to be negative. You can see that. Sometimes things are neutral also, but here everything is just negative because I'm starting with something that is neutral. Okay, so acid to conjugate base is minus H plus. Base to conjugate acid then would be plus H plus. Again, it can be neutral or not. So here going from negative, picking up a proton to become H2O. H2O picking up a proton to become H3O plus. So we're getting conjugate acids, okay? Conjugate acids can be neutral or positive, all right? So that's kind of what's going on here. So hopefully all of these examples help you out a little bit in identifying the conjugate acids and base. Okay, so here is a solved problem. Identifying conjugate acid bases and whatnot. So what is the conjugate base of NH3? Conjugate acid, sorry, what did I say base? I don't know. Anyway, what's the conjugate acid of NH3? So just add a proton and you get NH4 plus. What are the conjugate bases in the reaction below? The conjugate bases meaning that something that is negative, okay, but you can see everything is negative here, so which means that we need to focus a little bit on what has even lesser protons, okay, on there, because remember acids will give protons. So HSO4 here is going to SO4, so which means this is the one that's giving a proton. because see in the product, this is now HCO3, hydrogen carbonate, so which means that SO4 minus is the conjugate base. And here, this is the conjugate base because this is picking up the proton. All right, so this is the base. So I've written both as a conjugate base, but on the left-hand side, you generally tend to write base. On the right-hand side, you tend to write the conjugates. Okay, but here I just wrote bases. Maybe I should just change the problem and just say, which are the bases in the following reaction. So it might be a little easier. But generally, the bases are on the left-hand side and conjugate acid bases are on the right-hand side. Okay, so for the following reaction, which two substances are both acids? So now we're looking at the opposite thing. You know what? Just look for the positives. So much easier, right? So here is a positive, here is a positive. I was going to look for the negatives for the bases, right? But everything was negative. So I'm like, okay, now we got to do something else. But here, luckily, we have the positives. Okay, so the positives are going to be over here. And yeah, I will fix that arrow. I know it's kind of hanging above the reaction, so I'll fix it. Anyhow, so the positives are going to be the acids, that's that. And a strong acid leads to what kind of a base? And that's going to be a weak conjugate base. Okay, so just to kind of go over stuff. And these are the kind of questions you get also from this portion of acids and bases. Okay, so that's it. I hope you are feeling comfortable. A lot of this was just review, right, from general chemistry.